All right, good morning, everyone. Let's get started with today's class. So today we're going to go through the repeat and measure exercise. And I did upload the partial script and also a new data set for you on GitHub. So if maybe you want to do that first, if you want to do a Git pull just so you have that on your computer, you can go ahead and do that on the 2024 DSA. So again, a new data set and a new script that is uploaded to GitHub. Now, one thing I don't quite remember from last time, did you already create on your side the 06_RM GitHub repo on your, okay, so we're gonna do that. So again, I think the first step here is you can go ahead and do a Git pull on the 2024 DSA, right? So that's gonna give you the new data set and also new script. Once you do that, you can just leave it there for now because we're gonna create a new project. As you remember, the way that we've been doing this is we want to use Git and GitHub with these projects. So the workflow that we've been using is to go to your GitHub repo and create there first, and then you clone from there in your computer and then create the folders. If you need a refresher on that process, again, we have a few slides on that. So on our class website, that would be under, so the class of January 23rd, that's the installing Git, connecting Git and GitHub and so on. The slides for that class have the instructions on how to do this if you need a refresher. It's basically going to be starting on slide 4 of that presentation until slide 6, I believe. So the name of this is going to be 06_RM for repeated measures. So again, you want to create that first on your GitHub. That's what we're going to do to make sure that things get connected more easily. So 06_RM on your GitHub. You don't need a description. You can make it public. You check the box for add a README file. You add a git ignore for R. And then click on create the repository. After doing that on your GitHub, you click on that cold green button and choose HTTPS, copy the path. And then you come to your computer, launch any RStudio window, do a new project, version control in Git. You paste the GitHub URL on the repository URL box. The project directory name can be left blank. And then you click and you create a project as a subdirectory of, and then you want to browse to the main folder of the course where you would see the other projects in there. Once you do that, it's going to be cloned to your computer. And then remember to create the subfolders, code, data, and output inside of that project. Once you create those subfolders, code, data, and outputs, then you're good to copy both the data set and the code from the 2024 DSA that you just Git pulled. Copy those inside of the code and data for 06_RM. So in the end, you should have something that looks like this. Just here. I have a few more codes than you. You should only have the partial in there, but you should bring in that data set that I uploaded. So it's an extension of the previous data set. It's just that now it has more columns. We're gonna see about that. I'm just gonna walk through again the process, if you got lost somewhere. So the first thing that I asked you to do was to do a git pull on the 2024 DSA, so you would get the new data and new code. The second step was to go to your GitHub and create a new project or a new repository called 06_RM for repeated measures. So you create that first on GitHub, and then you copy that repository HTTPS path, and then create a project in RStudio using version control with that path. For full instructions, again, we have here on the January 23rd lecture. That lecture has notes on how to do this process step by step, if you need a refresher. Once you create, or once you clone this GitHub repo to your computer, then you want to create the subfolders data, code, and outputs, and then copy the script and data from 2024 DSA into the code and data subfolders of 06_RM. So in the end, your repository, your 06_RM folder should look like this. You should have the rproj. You should have the code folder in your case, just with the partial for the repeated measure. And then you should have the data the new data set in the data folder. All right, I think most of you have been able, at least here in Athens, that I can see you working on your computer or not. I think most of you were able to do it. If anyone is stuck, need help to get this done, let me know. I can give you one more moment, or I can help you out potentially. And if not, then I'm gonna get started. Yes.
The code is the good measures partial.
That's right, yep. All right, so I don't hear anything. I'm gonna assume that you all are good to go. So go, if it's not yet on your side, make sure to launch that rproj, clicking on the 06_RM. Remember, we always want to launch the project and then open the scripts from inside of that project to make sure that the paths are set correctly. So if you're not seeing yet the script popped up when you are in the correct project, you can come on the Files tab, click on the RBlue button to take you to the home of this project, and go inside of the code folder, and then click on the script to launch that on the side. I do want to make a quick note here that I'm sure, I would assume that you're all familiar with it already, but this is going to be perhaps the longest exercise that we've had until now. And for me, at least, it's really helpful to have the outline here on the side, because that helps me to navigate, understand where I am in the script. Because otherwise it's just continuous, lines of code that you can get lost of where you are in that structure. So if you're not seeing the outline, just make sure to toggle that on to see where you are, and that gives you a map of what we're going to do today. Also, this script here, I added more comments than I normally do. And I think that's because I wanted to give you a little bit more background of what was going on, what we're doing, and so on. So I have a lot of notes. Feel free to take your own notes on top of mine. But this is a resource that you can go back to and use for your future analysis of your own data. And so that's why I wanted to make it very explicitly explained. Okay, so, repeated measures exercise, a very quick review of what we're doing today. So last class, we had a lecture on this. We determined that if we sample the same subject, in our case, subject is your plot or your experimental unit. If we sample that multiple times over time or space, we cannot randomize time and space. And if we want a model that incorporates those variables of time and or space, that's a problem, because now we have potentially correlated errors because of the fact that we cannot randomize time and space. And that will be, it would basically, that correlation of the errors is going to end up on your residual of the model, the EIJK, or I think we've been talking about EIJKs, but it could be, EIs, EIJ, or anyways, the residual of the model is what I'm trying to refer to. How do we go about this? Is actually allowing the model. So the default linear model has the assumption of independence because we can randomize. And because it makes that assumption, then it assigns the correlation between the residuals to be 0. It does not estimate, it just sets it to 0. It doesn't even try to estimate it because it's based on that assumption of randomization. Again, here, time and space, we cannot randomize. So we need to allow the model to actually estimate those correlations instead of just setting them to 0. So we're going to fit different correlation structures to the error that will be, some are going to be, it's going to allow it to change, but in a very restrictive way. Others are going to be very liberal. Let it estimate as many correlation coefficients it needs to. There's going to be some trade-offs there of model complexity, model simplicity. We want to find the best model for our data. And the answer is, what we're going to learn here today is the process, but the result is very specific to this data set. So in your case, every time you have a new data set, you go through a similar exercise, you may get a different correlation structure to be the best for your case. Just a heads up. And once we identify the best correlation structure of the errors through this exercise, then that's the model that we check assumptions, that we make inference, extract means, pairwise comparisons, and so on. So that's what we're going to be doing here today. So I really had a, I guess, hard time to make the following decision. So my goal here was to keep with the same design that we've been working with in class and just turn that into a repeated measure scenario. That's what I decided to do. And the decision, I wanted to do that so you can kind of see the progression of the same data set or the same overall objectives and treatment structure, how that evolves, starting on a CRD, very simple, going to our CBD blocks fixed, our CBD blocks random, split plot blocks random, and now repeated measure on top of that. So this is really the most complex analysis that we're going to be doing when it comes to experimental design analysis in this class. And, in case this was not clear yet, if you have repeated measures, you're coming in with the hypothesis that your errors are correlated, and then this is how you test it. So this would be also something that you can do, even if you do not have repeated measures, but you do see a pattern on your residuals. Perhaps it could be related to correlations going on that you're not aware of. So this would be one way that you could fix a model that has residuals that don't fulfill the assumption. In this case, the independence assumption. So is one of the remedies to a model that is not behaving well. In our case, again, we already come in with the assumption that they are not independent because they were not randomized. So that's our assumption coming into this analysis. All right, so today, or maybe today and Thursday, we're going to fit different repeated measure correlation structures to a split plot RCBD design. So the same one that we've been working with in previous exercises. We're going to select the model with the best fit. And we're going to assess best fit based on the Akakis information criterion, AIC, and Bayesian information criterion, BIC. We're going to talk about these a little bit more in depth when it gets to that point. And then after we select the model, we're going to use it to make inference. So get means, pairwise comparisons, and so on. So I left you a lot of text here that I will some of it I'm going to repeat here in class, but I do encourage you to read through all of this as you are studying afterwards. So just setting up the stage again, we're going to analyze this as a two-way factorial in a split plot, as we've been doing on the previous exercises with the split plots, where the whole plot is potassium, split plot is nitrogen. So we have 9 treatments, we have 4 blocks in a randomized complete block design. And up until now, our response variable has been yield that was collected at the end of the season. So we had one measure of yield. For us to remain with this data set and just extend it to the complexity of repeated measure, what I decided to do was basically create some fake data that would be as if we were harvesting the same study 4 times. So let's say that, you know, that is something that you would see perhaps not as commonly with row crops, but perhaps you would see this with forage crops or a crop that you come back and harvest multiple times within the season. So I don't want you to get fixated too much on how are we harvesting. I think this was a wheat data set. How are we harvesting wheat 4 times? You know, that idea is just for us to create a fake data set, but more on the fact that we're measuring something 4 times in the same plots, right? So imagine that, I don't know, that we had like 12 row plots. So each time that you would be harvesting, you would come and harvest maybe one of those rows, but always within the same plot, right? So the same plot that was independently randomized to a treatment, we're coming back and measuring. You can think about this in different ways of other variables. So this could have been soil samples that you're taking over time. It could be vegetation indices, sensor data you're collecting over time. Every time you're collecting the same data over the same plots over time or space, you have repeated measures if you're interested in the time and space effect in your model. Okay, so in our case here, I'm just creating the scenario here that we would come at 4 different times in the growing season and harvest these plots in those times. So then the research question that we would have here is, you know, I do want to know what is the effect of time and how that is potentially interacting with my treatment effects like nitrogen rate and potassium rate. So I'm interested in the time of the effect and that effect of time in this analysis. So, you know, we could ask questions like, what's the interaction between treatment and time? Does the effect of treatment change over time? Or how do treatments compare at any given time points? Now, I want to make a quick parenthesis here to say that if you are not interested in the effect of time at all, you don't even have to do repeated measures. What will happen then is you would come on each one of the dates that you have and run a model just for that date. Completely separate model from the following date, completely separate model from the next 2 dates, right? So in that case, you may potentially have a data set that has time or days after planting or something column there, but you're always filtering that data to just be within a given date and just analyze that effect on that date. What that does to you is going to allow you to make to compare treatments within a date, but because your model does not have a time effect, you will not be able to make inference on treatments over time to say significantly treatment X increased and treatment Y did not. That you cannot say if you do it day-by-day models. In our case here, we're not doing day-by-day models. We're doing one whole model with all dates where time is part of that model. So that's what we're going to do here. Okay, so again, we have 4 harvest times, and because harvest time is non-randomizable, it requires for us to run repeated measure ANOVA. We're going to fit different correlation structures to that. And again, our goal here is to find the correlation structure that best describes the correlation in the errors. And we do not want structures that are more complex than needed. We do not want correlation structures that are simpler than needed. We want one that describes really well. And this is something that we're going to understand when we look at the AAC and BAC comparisons across different models. So what happens is if you let's say choose a correlation that's too simple, it's going to underestimate your standard errors of this analysis, which is the case when, for example, if you're on a default model that assumes correlations of 0, but in fact, you do have correlations of the errors, if you do not do a repeated measure type of analysis and you just go with the default of correlation 0, you are underestimating your errors. And again, you know, we had this talk before as far as well, I do want my errors to be small, so why would I increase my errors? That is not the point here, right? So the point here is to actually get the errors that are truly representative of what happened on the field, even if that means increasing it, right? We can try to decrease our errors doing other things like increasing replication, perhaps being more meticulous in the way that we apply treatments, collect data, and so on. But this is not the case, right? This is, we want the errors that represent what happened on the field. And if that means increasing the errors, then that's what it is. On the other side, if the correlation structure is way too complex than needed, then we're going to lose power because, and by power, every time we talk about statistical power, we refer to the power of finding statistical differences between your treatments. So finding a treatment effect. We decrease the statistical power here because we're calculating too many parameters that are consuming degrees of freedom that we wouldn't need otherwise because it's too complex for our case. So there's a balance here between using something that's way too simple, using something that's way too complex. We want to use the one that best describes our data, and that's what this exercise is going to be about. And if we inadequately model the correlation structure, that may result in biased estimates of variance of the fixed effects. So the means are not going to change. What is going to change is the variance or the variability or the error around those means, which impacts everything we do, right? Because those errors are what set our p-values in the ANOVA, is what set our p-values of the pairwise comparisons, and therefore the ladder separation. So getting the proper errors is key here, and that's what we're aiming for. All right, so let's begin our exercise. I left you here the setup chunk. So we have, I believe you may not have the NLME package. So if you run this chunk here and it says that you don't have an LME, then you go ahead and do an install.packages on that package. I think it should be pretty straightforward. I don't think it would give you too much trouble to install it. And once you install it, make sure you either comment off the install.packages or just delete it and just rerun then so you load an LME package in our session here. And again, NLME is a package that was developed by the same authors of LME4. LME4 was the package we were using for mixed effect models up until now, right? And that is Pinheiro and Bates. Those are the authors of the book that I share with you that has really great readings on all this and even other more complex analysis in case you want a reference for it. Okay, so I'm assuming you were all able to install if needed and also load an LME. If you were not, let me know. The next thing here would be for us to read in the data. So this data here is again the one that you just copied from the 2024 DSA. So it is a CSV file. So let's use a read_CSV to read that in. Open and close quotation marks so you can give the path you want to get outside of the code folder, inside of the data folder, and then get that weight, NK, bulk, RM for repeated measures. If you just run that and you print this object right below, you're going to see that it has 144 rows. It has 9 columns. So we still have a lot of the same columns as we had before. Now, one difference here is we have this column called DAP that stands for days after planting. This column here has 4 levels, 120, 130, 140, and 150. So now for each one of our plots, we have 4 yield values, 1 in each of these dates. One thing to notice here that I always want you to pay attention when you're running statistical models is that our treatment, block, N rate, K rate, whole plot, split plot are all double. And we do not want that. We want these to be factors, as we already talked about, because that sets the proper degrees of freedom in your ANOVA for these effects. So we're going to do a very light wrangling right here. I'm not going to have a whole session for wrangling because it's going to be very, just a couple of rows. So on this line here, we're importing the data and then doing wrangling right after it. So add a pipe. So I want to transform all these columns that I just told you into factor. What we could do, so we're going to have to use a mutate. I guess we can go ahead already and type that. What we could do is take each one of them, so you don't have to do what I'm gonna do next, but just to tell you, we could say treatment equals vector treatment, add a comma, break line block equals vector block, and so on, and do for all of them. I want to show you a shortcut. I don't think we've seen this yet, so it's going to be another trick here for you to have in your toolbox. So if you notice, I want basically starting on treatment and including block and rate, potassium rate, treatment, whole plot, split plot. I want to take all these columns and force them to be vector. Because they're all in sequence, we can use a trick here. So every time that we want to apply a given operation, in this case, vector, to a whole bunch of columns, we can use a function called across. It's a function from dplyr, I believe, where it takes two arguments. The first argument is going to be which columns you want to do something with them. In our case, we can just say trt colon, and I think the last one would be splot. So we're basically saying all columns between and including treatment and splot. So these are kind of like the ones I'm selecting, even though this is not a select. And then the second argument is what function you want to apply to it. So we need to give it a tilde, so it knows it's a function. And then I want to say vector, that's the function, and I want to have a dot right there. So that is basically just passing these columns into that dot. Is like just like a placeholder. So if you run this, now they should all be vectors and only the ones between treatment and split and splot. This sometimes is also useful if you have a whole bunch of columns that are for some reason interpreted as character, but they're actually numerical. You can come here, select the columns in this argument, and then say as numeric here. That also forces a lot of columns to be numeric. And there are other things you can do here, but this is just one example. Okay, so we transformed to vector the ones that we needed. The next thing that I want to do is we do need to have days after planting as numerical, as we already have, but we're also going to need to have that as categorical. So we're going to need to have both columns. In that case, I want to add a pipe here, create a mutate that I want to call fdap for vector days after planting, that I'm just going to say vector. This is just going to equal to vector DAP. So if you run it and you print that, now we should have both columns. Notice that we still have DAP, and then now we have FDAP. This is the difference of you not overriding the column name, right? So if I did not give that F, this would have overwritten on the DAP column by giving the F in front of it, or really any other name. It doesn't have, there's nothing special about F, but any other name here, it creates another column. So we're not overriding on DAP. All right, so let's, as always, let's do some quick exploratory data analysis. Let's look at the summary first. So really the only thing that is numerical now is, well, I guess there are two things in numerical. So yield is numerical, so that gives us the statistical summary. We're seeing here this in kilograms per hectare. And then days after planting is also numerical, but it is an integer column, right? So we have 120, 130, 140, 150 days after planting, even though it gives us a statistical summary like this. All right, so let's create some intuition of how this data set looks like. Let's make a plot to look at that. So I'm proposing that we use a ggplot where we bring the data set and we have the factor days of planting on the X and the yield on the y-axis. If we just run that, as maybe you're already expecting, ggplot just creates you the canvas because we have not asked to add any geoms yet. So it puts the axis properly, the ranges of the axis, but nothing is in the plot yet. So what I want to do here is I want to create box plots of these distributions. So we can just go ahead and do a plus geom underscore box plot. This is what it looks like. So we just have the box plots at this point, but what I mean, it's basically just showing us 4 box plots, one for each one of the dates. There may be, well, I guess let me ask you this, what is happening with all the observations we have? So the 144 observations where we have different blocks, different N rates, potassium rates, and so on. So if you think about it, it's just bringing them all together. So anything that was sampled that was harvested at 120 days after planting, all that is falling here, and then the same thing for the others. For us to break this a little bit more and have an idea of how, so let's say if I wanted, well, let me pose this challenge for you. If I wanted to have a plot for each treatment and still have yield on the y-axis and days after planting on the x-axis, but have one plot per treatment, how would we do that? Okay, so Pramod is saying facet. So let's do a facet grid. So I want to add the point, give it a tilde. I just want to print the data set below so we take a look at the columns. I guess there are a couple different ways we can do this, but there's one that's simplest, at least coding wise. Which of these columns would go after that tilde? Okay, so I hear K rate, I hear yield. So yield is already on the y-axis, right? So it cannot be yield. Yes, treatment name, I think, is the one I'm looking for. So you can play around with this and see what would happen. So if we were to add K rates, you would just do that only for K rates, but now all the nitrogen rates are within here. If I want to see all the treatments, it would be treatment name, which we have a column that way, like that. So here we have one panel for each one of the treatments, which are named on top of the panels, and then we have the box plots. So now we have, if you think about it, well, let me ask this someone else. So I'm not showing the points behind the box plots, just the box plots themselves. So when we did the previous plot that we just have days after planting without the facet, we basically had all observations within a given days after planting as part of that box plots. So now we have treatment names on top. We still have days after planting as a factor on the x-axis. So how many observations do you think there is in each one of these box plots? Four, right? And why four? Okay, that's one way of getting to that. We need to set replication, yes. So now we only have 4 observations because it's the replication or the blocks within each one of those treatments and sampling dates. So if you think about it, what we were doing before when we only had one harvest date, imagine that we only had one box plot per panel here. That's what we had before. Now we have 4 harvest dates. That's why we have 4 box plots per treatment in this case. All right, so the scenario that I created, yield was measured 4 times in 120, 130, 140, 150 days after planting. One thing to make a very important point here is I made this in such a way that we could explore all of the potential correlation matrices. For that to be the case, notice that the interval among the different harvest times is the same. So it's basically 10 days difference between each one of those harvest times. If this would have been different intervals, right? So let's say that the last one here was 160 perhaps. So it's 10, 10, 10 day, and then 20 days. We would not have been able to use some of the correlation structures because some of them do require to be equally spaced. In our case here, in our example, they are all equally spaced, so we're going to be able to try all of them. And if you want to have a reference of which ones are and which ones are not, you can go back to the lecture notes. We had some explanation about that. But if you recall the correlation structures, there are 2 groups. There are the serial and the spatial. The serial are the ones that are applied mostly to temporal data, so one-dimensional repeated measure temporal data. Some of those could only be used with equally spaced intervals. The spatial correlation structures, which can be used also with temporal, but are very useful for spatial data in 2 dimensions, repeated measure, those can be applied to non-equally spaced data. So there's a distinction there. I just wanted to bring this up here so you're aware. So with that, because they're all equally spaced, we can use all of these structures that we saw in class, which again, here are the ones, the serial ones. So that the first one is compound symmetry, which is the simplest of them. There's the general, which is the most complex of them. There's autoregressive of order 1, AR1, very common in agriculture, and autoregressive of order 1, moving average. So this is also one that is common that we're going to test. These are all serial correlation structures. Then we have the family of spatial correlation structures, which again can be used for temporal data, but are necessary if you have spatial data. You cannot run spatial data with the serial ones. It has to be the spatial correlation structures, but if you have temporal data, you can use both families. So we have here the exponential, Gaussian, linear, rational, quadratic, and spherical. So what I wanted you to remember from this is if we go back to the lecture, I just want to show some of those slides again, just for us to have a refresher. So the spatial correlation structures that we're seeing there are the ones that are going to try to fit this to our data. Where we're going to have the distance here is going to be the distance in time. So we're going to have 0, and it's going to be the relative difference. So going to be 0, 10, 20, and 30. 0, 10, 20, and 30. I think that's right. Because we have 120 days, 130 days, 140, 150. So just the difference between those. So that's what would be on the distance. And then the semi-variogram is related to that correlation. So it's going to fit these different models to our data and trying to estimate the range of that correlation, which again, the range is just the distance after which after each point your correlation plateaus out. So the range here for all of these plots, they were created with a range of 1. So on the x-axis. So if you were to come, maybe here's the easiest one because of breakpoint. If you come here, the range is 1, and all of them are basically set to 1. But we're just fitting different curves to our correlation structure and see which one is the most appropriate, if any. Okay, so if you remember, the steps here would be to first fit our default model that assumes the correlations to be 0, right? So that is our first step. Up until now, we've been using the function LMER from the package LME4. So right now, I do want to show you, so the repeated measure exercise, we're going to be using a different function from a different package. But I do want to show you that at least until the point that we were last time, which was a split plot with RCBD blocks random, these two functions can be used to run the same model. I want to show you what that looks like so we can understand this transferability between both of those packages and functions. The reason why we're changing to LME now for repeated measures is because LME will allow us to give it different correlation structures, which is not, I think it's not even possible with LMER. Perhaps it is possible, but it's not as intuitive. So that's why we're changing to LME so we can fit the different correlation structures to repeated measure data. Okay, so another thing I want to point out here is, so try to follow me here on what we're thinking. So we have the blocks, we have the whole plots, we have the split plots. So block, potassium, nitrogen. Now, if you think about it, you could interpret the time as even smaller units within the split plot unit. So it's almost like it's a split plot where time is the smallest level. Now, again, the problem is that time is not randomizable. So we're gonna trying to model that here. But because now we have this other inner level that is time, we can basically treat this error as a split plot. I mean, not the error, the random effect of this model as a split plot. And I guess let's get to the code, and maybe that's going to be useful or more easier for you to understand what I mean by that. So if you come here to the code, we're going to use the LMER function just so we keep with, at least you see the transferability of LMER and LME. So let's call the LMER function. I just want to print here our data set so we can just copy and paste the columns. Our data set is RM_RCBD_DF, I think. Yeah, that's it. So I just want to print that so we can copy and paste column names. So as before, we're going to be explaining yield. So we can copy yield and paste there, give it a tilde. The first thing that we want to give here is the fixed effect side of the model. So that would be K rate, asterisk, N rate. This is where we stopped on the fixed effects last time. Now, because we have a time component that we want to model, we're going to add that time component here. So add another asterisk, and then we're going to add here the FDAP for factor days after planting. So this is going to be our fixed effect side of the model. Just a refresher. Now we have a three-way full factorial interaction here, right? So if we were to do this by hand and not use the asterisk, we will first have to say K rate plus N rate plus FDAP, then all the two-way interactions. So K rate plus N rate, K rate plus FDAP, N rate plus FDAP, not plus, colon, and then plus the three-way interaction. Because we're using the asterisk, it's doing that for us, right? So just as a reminder. All right, so this is the fixed effect side of our analysis. Now we're going to call the random effect side of this model. So if you remember to do that in LMER, I just want to break code a couple times. We use the one vertical bar notation. We start off with the largest unit, which in this case is block. So block, then / to mean that the next thing is going to be nested in block. The next thing should be our whole plot unit, which is in the K rate, kilograms per hectare column, right? So potassium rate is the whole plot. It's nested in block. And this is where basically we stopped on the previous example that we did a split plot RCBD blocks random. This is where we stopped. Now, because we have another, and I guess this is an important point to make. We stopped here because the last level of that complexity you leave out of the random effects because that goes to the residual. So in this case here, before we have repeated measures, the last level of the complexity was nitrogen rate. So we did not include nitrogen rate here because that falls into the error. Now we have nitrogen rate and days after planting. So now we have another level. So now days after planting is the last level that should go into the errors, meaning that now here in this random effect, we should specify that is also nitrogen rate is nested in here. So we're saying nitrogen rate is nested in potassium rate, which is nested in block. And then the time effect that would be the smallest level is what is going to the error. And that's why we check the correlations in the error, because that effect is falling in the error. Okay, so the last thing here is if you get outside of that parentheses of the random effect, you just add a comma because we just need to say what's the data that this is all in. So we say data equals RM RCBD DF. And then if you want, you can print this. It's going to be a long print, but it's just going to be the same type of output that we're looking at when we use LMER. So we have the random effect side of that model. We have the fixed effects as coefficients, and that's it. So this is how we would have run the default model in LMER. And again, I am showing this to you because I want you to see how the LMER syntax translates to LME syntax, which is what we're going to use to actually do repeated measure analysis. All right, so yield explained by all the fixed effects plus the random effects in this type of syntax. Just want to close this output so I don't have to be scrolling a lot. So now let's go to the next chunk, and I want to show you how we will fit the same model, but with LME, and how that is a different syntax. So give it the assignment symbol, we're going to call the LME function. Again, I just want to print the data below so I can copy the column names. So the RM, RCBD, DF. So the beginning of it is similar. So we're going to say yield explained by then the fixed effects. So potassium rate, N rate, and FDEP using the asterisk. Remember that. So in LME, which is what we're using right now, the formula side, which is what we're specifying, only on this step of the function, we just determined the fixed effect sides. Now the random effect has its own argument. That's one of the differences between LME and LMER. So we add a comma here, break code, and it has this argument called random, which you need to say tilde, one vertical bar, and then all that structure that we created before. So block / potassium rates / N rates. So again, the difference here in syntax between LMER and LME is that in LMER, the fixed and random effects of the model are specified in the same argument. Here in LME, we specify the fixed argument in the formula, or the fixed terms in the formula arguments and the random terms in its own random argument. So there's light difference here. And then last thing, we just need to say, where is the data coming from? So data equals to RM RCBDDF. So if you run that, and if you were to print this, these should be the same model. They have the same, they fit with the same fixed effect structure, the same random effect structure, and at least until now, we have not told LME to change the correlation matrix of the error. So it is the default one, which is also what LMER does. So right now, these two models are the same. From this point on, I'm just going to be using LME because again, LME allows us to change the correlation matrix, but I did want to show you the correspondency between a model in LMER and LME, so we connect with what we've been doing up until this point. Okay, any questions about this? All right, I don't hear anything, so let's get to the actual repeated measure type part of our exercise. Oh, I guess before we do that, this is going to be interesting. So if you run the ANOVA uppercase A function on the default value of the LME, so from this point on, we're forgetting about the LMER model. We're just going to be working with the default ones coming from the LME function. So if we run the uppercase ANOVA, let me ask you all to think about this, and I'll ask some of you to help me to answer this. So if we did not know about repeated measures, this was the model that we were using without even trying to fit different correlation structures. And we looked at this ANOVA and we were ready to perhaps, we should always check residuals, which I'm not showing you at this stage yet. But let's say, we were ready to extract means and do pairwise comparisons. What term or terms would you extract means and do pairwise comparisons looking at this ANOVA and assuming an alpha of 0.05, so 5% significance? Okay, so Benita said interaction between K rate and N rate. Oh, maybe I forgot to run my options here. It could be that. So maybe let's just make sure that we run that options. I think I forgot on my side. Maybe you didn't yours. And let me run again this model. And now they should be the same. You got again the same? Oh, between having the contrast or not? Anyone has a different ANOVA table as far as p-values especially? Okay. So looking at this and assuming alpha 0.05, how would you extract means and do pairwise comparisons? What would be your decision?
That's here, wait, for different things.
Okay, let me go with Anis first. So you said interaction of what?
And curious.
Okay, N and K rates, right? Because, okay, for different days after planting. So what I would do here is I would break down this interaction by itself and then have a different table plot just for the days after planting, where we're averaging across everything, right? Because that is what is being significant here. So this at alpha 0.05, this is not significant. So I would not break that three-way interaction. I would just break this two-way interaction and then this main effect. Okay, what about if I was using a alpha value of 0.1, 10%? How would you decide to break your interactions? Arminder, you wanna give your thoughts since you were ready? The last one, right? Yeah, and you should really only break this up when it comes to you interpreting your results and making inference. Of course, people would still show all of these effects by themselves, right? So they would still show K rate by itself, N rate by itself, and everything else. Which, I mean, I think it's okay if you just want to give your audience an idea of how those are changing, but you should really not be discussing too much these main effects, or really even the two-way effects. Well, first off, because here they're not significant, but also even if they were, you do want to show and make inference on the most complex interaction that contains those effects, right? In this case here would be the three-way if we were to use a alpha 0.1. Okay, so the model that we just ran has time on the fixed effects, and it is assuming the default correlation structure, which is to assume zero correlation between the residuals. One way that we can check, especially with temporal data, is to look into the empirical autocorrelation function, which is going to give us, is going to be applied to the within group residuals. So what do I mean by that? This function here is going to look for the correlation at the deepest level of the model, or in other words, at the smallest level of the hierarchy, or in other words, days after planting in this case, right? Because that's the smallest thing that we're not including in the random effects. And because of that, is falling into your residuals, and the plots and changes in the correlation structure that we're doing are all based on the residuals. So the autocorrelation values are calculated using pairs of residuals within the innermost grouping level, which again, in our case, is going to be the residuals that are falling in the EIJK that are related to the time component. And this is useful for us to investigate serial correlation models for equally spaced data. So let's run that function here and see how this looks like. So the function is called ACF. It's coming from NLME, where we give the first argument is the model that we want this for. So mod1 underscore default is our model. I want to change the residual type that it uses. So it has an argument called res type that I want to change to N, which indicates normalized residuals. So if we just run this, it creates this for us. So it's using all pairs of residuals between the lags 0, 1, 2, and 3. In this case here, 0, 1, 2, and 3 are basically meaning 120, 130, 140, 150 days after planting. If we had more or less levels, they would be changing here on the lag. Now, if I want to make a plot of this, so let's add a pipe, and it's not going to be a ggplot, just for simplicity's sake. We're going to call the function plot, which comes from base R. And if we just run that, this is what it shows us. So it's the autocorrelation on the y-axis and then the lag on the x-axis. What we see here is we have a very positive, high and positive correlation on lag 1, which every data is going to have, because lag 1 basically means correlation of that observation with itself. So it should be high because it is with itself. But then at different lags, so 1, 2, and 3, meaning the different harvest dates, these are the ones that we're going to be looking for correlation in the error structure. One way to help us with interpreting this plot is to add significance bands. So if you come to the plot function, it has an argument called alpha. I want to say alpha equals to 0.01. So we're setting a 1% significance level to these bands. So these bands now are basically showing us or helping us to interpret this. And the way to interpret this is if a autocorrelation bar that we see at each one of the lags is within the bands, then the autocorrelation is non-significant. If it is crossing the bands and going beyond them, then the autocorrelation at that level is significant at that lag. So we see here that on our default model, there is significant autocorrelation at lag 1 and 2, not in 3. And at lag 0, we're always going to have autocorrelation because, again, it is the residuals with themselves. So just through this plot, we do conclude that we have some level of autocorrelation to errors, and we need to do something about it. I think everything I said is what are in the notes here, so you can refer back to that. Okay, so we ran the model with time and with the default assumption of correlations being 0. We checked that autocorrelation plot, and we saw that at lags 2 and 3, which are the sampling or the harvest dates, the second and third level there, we're having significant autocorrelation of the errors. So now let's try to fix it. How do we fix it? Is we allow the same model to have a different correlation structure. The first one we're going to try, again, is the simplest one. It's called compound symmetry. So I do, let's see, maybe if you go back to the previous model chunk. So if you go back to this, the mod 1 default chunk, you can just copy all that. Okay, so if you go to the mod 1 default, you can just check, you can just copy the LME starting on L and then ending at the last parentheses. Just copy that and go back to the last chunk we were in, which is the mod2_CS. You can give it the assignment symbol, paste what you copied above. So again, it's just the LME call with yield being explained by potassium rate, nitrogen rate, and days after planting as a factor. Our random effects being N rate nested in potassium rate, nested in block. Our data. And now we're going to allow it to change the correlation structure to the compound symmetry one. The way we do that is, it could be anywhere here. It could be after data. I just want to do right after random, but it doesn't have to be, but it's just what I did on my side. I think it's a little bit more intuitive. So it has an argument called correlation. This argument does not exist in LMER. That's why we're not using LMER for this exercise. So here on this correlation argument, we can give any of the, I guess in our case, 9 that we're going to try, functions that specify different correlation structures. Compound symmetry is the first one on the serial correlation structures for time variables. And the way that we call it is a function called core. If you start typing core, you're gonna see, I mean, there's gonna be some other stuff, but you're gonna see a whole bunch coming from NLME. Those are all the ones that we have access to. So this one is the core comp sim. And it has an argument called form, which is what we want to say, like, what is the variable that is our repeated measure variable in this case? So we're just going to give it a tilde and say DAP. Now notice that DAP is that numerical column in our data set, and FDAP is the factor. I'm using the factor version on the fixed effect side of things, and I'm using the numerical one here on the correlation. The reason for that is if I were to use the FDAP in the correlation as well, FDAP is a factor. So even though the factors are named 120, 130, 140, 150, but that interval distance will not be considered if I'm treating as a factor. It is, the distance is considered if I'm given DAP on the correlation as a numerical, because now it looks at the numerical column, it sees the actual numbers, and it can use that distance between them to calculate the correlation. I guess in my case, I need a comma here. Don't forget to add the comma after that correlation, so your model runs well. Okay, so just a quick recap then. We're using correlation here, where we are telling it to use the correlation comp sim, which is a function from NLME package. And we're saying that the level that we have, or the variable that represents that repeated measure is depth doing this. If we run that and we print this output just to look at what that is, there's going to be, so it's showing us all the fixed effect side of the model. It's going to give us here the random effects for each one of the levels. So we have for the block, for potassium, nested in block, nitrogen, potassium, nested in block. And then it has this extra part of the code telling us about the correlation structure. So it's telling us that it was a compound symmetry. That's what we asked it to do. And now it's giving us an estimate of rho, which it was not doing before. So the estimate of the correlation is 0.11 in this case. So this is an extra piece of output that we did not have before. All right, so what we're going to do now is ask again for the autocorrelation plot that we did for the default plot or the default model, but now apply to this model where we allow the correlation to change according to the compound symmetry structure. I left you the code already because it's the same code. We're just changing the model here. If you run this, this is what we see now. So we see that now the model was able to decrease a lot this autocorrelation of our observations. So this is one of the metrics we're going to use to check what is happening with these different repeated measure matrices. So one of them is doing the ACF plot or ACF and plotting that to get to know if our correlations have been fixed. So in this case, it looks really good, right? Before, I just want to show you the previous plots. This is what it looked before, right? So now the autocorrelations are really small, which is something we want to see. So it's a good sign. But that's not the only thing. It's not the only metric we use to say this is the good model, right? So let's go through the next metrics we would use to assess this model here. One thing that we can do is to ask for a confidence interval on rho. What we want to see is a confidence interval that does not contain 0, because that would mean that the coefficient rho is significantly different from 0, which is what we would hope to have if our errors are truly correlated. So here, the function that we're going to call is just intervals, plural, where we give the model. So the model is mod2 underscore CS. If we just run it that way, it's going to give us intervals for the fixed effects, the random effects, and the correlation structure at the end. That's okay. There's nothing wrong with it. Just to make it a little bit shorter, we can just we have an argument inside of intervals that we can ask to just get the variance covariance related intervals, so it would not give us the fixed effects. So the argument name is called which. And then you open and close quotation marks, you can say var dash cov for variance covariance. If you run this, it's still gonna give you the random effects. So it's basically inhibiting the fixed effects from being printed, which at this point, we really don't care about fixed effects. We're just trying to see what is the best correlation structure. So if you look here in the end, it has, so first gives you the output for random effects, which I'm just skimming through them because again, right now I'm interested in the correlation structure. So we see here that the correlation structure, it has a line for rho, which was the estimate that we had of 0.11, but then it gives us the lower and upper confidence levels of that. If you look at this, the lower confidence limit is negative and the upper is positive, meaning that our rho confidence interval includes 0, meaning that it's not significantly statistically different from 0. Which, is not a problem in itself, but it's just something that we want to check and make sure that we understand if it is like a high correlation that is like way different from 0, or if it is something that has some correlation, but it is very close to 0, perhaps not even different from it. All right, so next thing I want to do now, are you guys getting the same results? Oh, really? Okay, is someone not getting the error? Okay, so well, that's lovely. Okay, so it seems like some people are getting errors on the interval and some are not. Are you including the mod 2 CS in there?
Yeah.
Or I guess you were, I mean, people that were getting error. You didn't? Okay, of those that had an error. I'm trying to think. Yeah, that's always a possibility. Well, I guess if you are getting an error. Let's see, Renalisa, are you still getting the error? Okay, so the only thing I can think of that could have impacted that is whether or not you ran the options to change the contrast types. Because the data is the same, the package is the same. So maybe try running these options here again on the chunk that was under model 1. So if you run that, and then make sure you rerun the mod 1 default, so it applies to that, and make sure that then you run your mod 2 CS chunk as well. And then try to get the intervals. Hmm?
Still giving the same error.
Still after running the options?
Yeah, because I have the whole code.
Okay, it may be a different version than perhaps of an LME.
Oh, yeah.
Because I don't think I reinstalled an LME on my side. Maybe I have an older version. Well. Yeah, let me reinstall my NLME and check on that. So if you change to which fixed, then you get, but you don't get but that then just gives you the fixed effect, right? It doesn't. Yeah, I mean, if I change this to fixed, it should be the same as what you get if you change to fixed. But it does not give you then the random component, which is what we're interested. So let's do this. For now, let's pin it. And the reason why I'm saying that is because on my intervals, whoever is being able to run the intervals on this model, you're seeing that rho is not significantly different from 0. It could be because, there's probably some difference version between my NLME and yours. Probably mine is outdated. I'll rerun this after class and make sure that that's the case. But if you're because this is going to happen again in other models, and this can happen when your correlation estimate is very small, is very close to zero. You could have a hard time running intervals because it's not being able to calculate that. Yes.
There's more error. I do see difference in the reduced group standard error.
In the within groups in the area, you're seeing differences?
Yes, because.
Okay. Well, so maybe let me go ahead and reinstall on my side. Let's do that. So session, restart our. Okay. So install packages and LME. All right, so I just reinstalled here NLME. Let's see if that's what's causing the differences here. So my environment is empty. Set up and ring me. Okay, so I'm still able to run. So what I did here to try to troubleshoot, I reinstalled an LME on my side and then restarted the whole exercise. I'm still being able to run intervals on mod 2 CS. And this is what I'm getting as far as correlation structure and within group center error.
We have the EST same value, but lower and upper is given for us.
Like how different?
Well, the correlation structure is the same, but the within group standard error.
2.38 something.
Yes, I have the same.
2.38 here. So 2.38 and what's the power here?
Same.
Okay. So I'm not sure why that's happening.
Upper is also. We have been like power 4 and.
Power is
Power is 4. Okay. I'm not sure. I'm not sure why that is. I think, well, let's see, someone had a comment here. I got the same numbers you did, Dr. Okay, so Austin got the same numbers. So we have like 3 different. I have same outputs as yours, Sikra said. All right, thanks, guys.
On the section not working.
Are you getting the same as mine?
Not working, it's giving error.
Yes, give me.
Intervals, okay.
After reinstalling.
So let me take a note here. So some people got errors. Some people no errors, but different outputs. So for us to not spend a lot of time on it is very important, and I do want to understand why this is happening, but at the same time, I want us to keep moving forward. So for now, let's just pin this difference. And I do want to ask you all that if we get to a point where the model so maybe there's more towards, well, let's do this. When we start comparing the models with using, which is the next step, and you get a different interpretation, so the numbers may be different for now, but if you get a different interpretation than me, let me know, okay? All right. I'm getting error 2, and if I do which fix is running, but not when I change. Yeah, so in this case, if you change which to fixed, it only prints the fixed intervals or the intervals for the fixed effect estimates, which is not what we care about at this point, at least. So for now, you can just keep the Varkov and just take note that it did not run for you. That's fine. Because well, we'll see how things progress since we got 3 different scenarios going on in class. But we'll troubleshoot that later. So for now, all I ask is if we get to a point where I say, I would choose this model over this, in your case, the interpretation is flipped, that's when I need you to let me know, because that's gonna change the way that we move forward with things. Even if the numbers are different, but if the interpretation is changing, then let me know. All right, so on my side that I get to run the intervals on the mod 2 CS, and I do see that row includes 0. Sometimes if your correlation is small and is really close to 0, intervals may not run. And that happened to me with other models that we're gonna be seeing here. So just because it doesn't run, it doesn't mean it's bad. I guess I'm intrigued to see if you get different interpretations than me, especially on the next chunk. Okay, so just to give you a quick overview of this first model, because this sets the stage for all the other models. The other models are just going to be the same workflow, but different correlation structures. So let's make sure that we get the process right, at least understand the process right for this first one, and then we're going to be good for the next ones. So on the model 2, we fit the same fixed effects, we fit the same random effects. We then change the correlation to be the correlation comp-sim for compound symmetry with a form that's tilde DAP numerical, right? So we're allowing the error matrix to change according to different DAPs using the compound symmetry type of error structure. Then we looked at the autocorrelation plot, and we see that on this plot here, it did improve because now autocorrelation LX 1, 2, and 3 are small to negligible. So did a good job there. That's not the only metric. We would come into the intervals. If intervals run for you, you want to make sure to check if your interval includes 0 or not. If it does not include 0, then that correlation was significantly different than 0, which is what we're looking for here, is to find if that is the case. If it was not different from 0, which is my case here, it means there is some correlation there, but maybe at least there is some correlation that this structure is being able to find, but it is small, right? And not significantly different from 0. The next thing here is for us to compare the models. So our mod 1 default is going to be our baseline. That's what we're comparing to, and then that's what we're going to use as the model that is going to allow us to understand if a given correlation structure is improving or not based on that model. To compare models, we're going to be using again AIC and BIC. We're going to be getting those metrics from this function ANOVA. I want to, this may be confusing, so I do want you to pay attention here. We have already talked about 2 ANOVA functions. One uppercase, which is the one we're using when we want to check the ANOVA table. And we have already talked about a lowercase one, which is not the same as this. This lowercase ANOVA is coming from the NLME package and is specifically to be used with LME objects, which are models or objects that are assigned an LME and assign a LME model output. So mod 2 CS, if we were to ask for the class of it, it would be LME, right? And it is LME because, oops, tell me that. It is LME because we ran it with LME function. If we check the class of mod 1, well, I guess I haven't run on this script. Let me just run that very quickly just to make this point here. So this mod 1 default LMER should not be an LME object because I ran it using LMER, not LME. It's a very subtle difference, but it makes a difference because on that ANOVA function we're going to be using next, it does not handle LMER objects. It only handles LME. So if I were to check the class of this object here that we created using LMER, so it is LMER mod, LME4. It is not LME. Again, a small difference, but important. All right, let me browse through again. So I was here, model 2 comparison. Okay, so we're gonna be using the ANOVA function from the NLME package and giving both of those models. The output is going to include different things where some of them are the AK key information criteria, AIC, and the Bayesian information criteria, BIC. Those are two of the metrics we're going to be using to determine if our models are improving or not. So these fit metrics are intended to use for comparing models that are fit using REML, which is a default in LME, and they have the same fixed effects. So our models, all the models, well, up until now, we only ran two of interest. So mod 1 default and mod 2 CS. Both of those models have the exact same fixed effects, exact same random effects. They just have the correlation structure different. And that's when we want to use metrics like AAC and BAC to compare models. For both of these metrics, the lower the value, the better. Okay? So keep that in mind as we are going to be interpreting these values. So the smaller these values are, the better they are. So you can kind of think of, so AAC and BIC. So let me take a little bit of background here. If you do a linear regression, let's say, like let's get outside of this example completely, just think of a linear regression. So you have yield explained by, I don't know, soil pH. Then you get an R square, let's say 0.5 of that correlation. Then you add now soil potassium. That correlation goes from 0.5 to 0.6. Now you add nitrate in the soil. That goes from 0.6 to 0.7 and so on. R square will always increase when you add a new variable, regardless if that variable is useful or not. Even if that increase is very small, R square will always increase. However, there is a concept, I don't know if you came across this, we have not seen in this class yet, of adjusted R square. Adjusted R square is a version of R square that penalizes variables that if you include in the model, they take a degree of freedom, but they're explaining very little variability. In that case, so R square of a correlation of a regression will always increase as you add variables, even if the variables are not useful. Adjusted R square will not. It will reach like an optimal R square. And if you keep adding things that are not helping you to explain, it's going to start decreasing then. AAC and BIC, even though are different metrics, completely different metrics, but they follow the same thoughts. AAC and BIC will only decrease, which in this case, remember, lower is better. They will only decrease if the more complex model that you are calculating extra parameters was actually able to explain more variability in relation to how many degrees of freedom it consumed. So we have this balance here, so that is what's going to help us to find models that are just right for our data and not too simplistic or too complex models. In this case here, when I say models, I'm just referring to models with different correlation structures. But this concept of AAC and BIC applies to any model fitting exercise. Whenever you're interpreting them, they're going to be weighing how many variables there is, how many parameters are being calculated, but also with how much information you're gaining from that. If you are consuming a lot of degrees of freedom for adding something and it's not helping to explain a lot of variability, these numbers are going to go up, which is bad. Okay, so just keep that in mind. Okay, another note before we actually do the comparison here. AIC and BIC are related metrics. They're calculated slightly differently. I'm not even showing you the formulas. If you want to know more about this, I can give you some resources, but the goal here is for you to understand how to use them. So AIC is a little bit more liberal, meaning that it's gonna, if you add a variable that explains a little bit of variability, AIC may decrease by an amount and BIC may decrease by a smaller amount. So BIC is going to be more, AIC more liberal, BIC more conservative. So it's going to be harder to convince BIC that a model is better than it is going to be to convince AIC, if we think about that way. And sometimes they do not agree. Sometimes maybe AIC tells you that a model improved and BIC tells that it actually did harm to your original model. So just also keeping that in mind as we go through this exercise. Okay, so let's finally get to this comparison here. So again, the function is called ANOVA. We're just gonna give it both of the models. So the first one is the mod1 underscore default. We can just give a comma. I want to break code. The second one is mod2 CS.
Hey, Dr. Bastos,
Yes.
you may have said it before, and forgive me if you have, but could you say again the difference between capital A ANOVA and lowercase a ANOVA?
Yeah, so in the past, we have used both capital A and lowercase a ANOVA to get ANOVA tables. The difference being the uppercase ANOVA was doing the type 3 sum of the squares, which is what we want. And the lowercase ANOVA was doing another type of sum of squares that we do not want to use. In this case here, this ANOVA function is actually completely different from that because it's now coming from the NLME package. And this ANOVA function from the NLME package is going to help us to compare models that we're fitting with different correlation structures. So the lowercase, so the same named function, ANOVA lowercase, that we used before was coming from a different package. I think it was stats package or some base R package. So they are the same name, but coming from different packages. Remember that can happen. In this case here, this lowercase ANOVA is coming from an NLME package, which allows us to compare models.
Yes, sir.
No, go ahead.
So it is showing me the different ANOVA dot NLME, like it's separate for the simple ANOVA is with the stats.
Is it showing you this? Yeah, this is what we want.
No, like the simple ANOVA is in the stats packages.
Oh, okay.
The NLM.
So
For NLME, it's different.
if
It's
you-
dot NLM.
yeah, so you can either, so if the ANOVA function that you're running is not giving you this, then it's probably coming from another package. One way to fix that would be to do NLME : ANOVA, because this is forcing then for this ANOVA function to be coming from an NLME package. This is what we've done in the past with the select function, if you remember. So the select function is a very common function name across packages. When we're using that in wrangling and we want to specify for that to come from the dplyr package, we use the notation dplyr : select. This is the same approach we're doing here if you have to. As long as you're getting, oops, it's actually not coming from there. What's going on? Let me see. Let me start typing here.
Yeah, I was.
Oh, okay. I know, okay. Yeah, so if you're not getting this output here by default, you may need to do LME. Then you should be getting that. All right, was everyone able to get this output? All right, so let's walk through here this output very, let me see here. Our class goes to 11 or 11:10?
No.
Okay, awesome. All right, so let's walk through this output here very slowly because I do want you to understand what's going on. So it gives us a row for each one of the models that we give it. We can give as many models as we have. We're going to be doing that as we fit more models. It gives those models a number, which I guess is not very, very important. It gives us a degrees of freedom column, which we're going to get back to it in a second. It gives us the AAC, BIC, and then it has some other things like the log likelihood, the test, the likelihood ratio, and the p-value. What I want to bring your attention to is really 3 columns here: the DF, the AAC, and the BIC. The others I am basically ignoring for this exercise. You may need to use them in different settings. For this exercise, I'm just going to be referring to DF, AAC, and BIC. All right, so a few things to note. Remember that I told you if you fit more complex models that are calculating more parameters, those parameters are calculated at the expense of degrees of freedom. So if you look here, the difference in degree of freedom between the default value and the compound symmetry correlation structure is that compound symmetry is taking up 1 more degree of freedom. That is to calculate rho. This is going to that estimating rho, it's using 1 degree of freedom. So it's using a degree of freedom. Now let's look at AAC and BIC to understand if that is being a good use of that degree of freedom. If that row is actually helping the model. So our default model, our baseline here has this value of AAC. Before I compare it to it, I just want to tell you that AIC and BIC values, the magnitude of them really don't matter. This is going to change if you change the model, if you change the data. Sometimes like your base model is even a negative number. That magnitude of the value is not important. What is important is the relative difference between the models you're comparing. So in this case here, we see that AIC, and remembering lower is better. AIC of the default model is 1335. AIC of the compound symmetry went up, is 1337. So even though the compound symmetry accounted for the autocorrelation that we saw on the autocorrelation plots, so this is what we want to see. It accounted for that autocorrelation at legs 1, 2, and 3. Our intervals, at least in my side that I could see it, that row was non-significant. And we see here that perhaps because of that non-significant row, it took a degree of freedom to calculate it, but it was actually not explaining a lot of correlation because it was very little correlation. So our AAC went up, meaning that it was a worse model. If we look at the BIC, the values are slightly different, but the interpretation remains the same. The BIC went up even higher for the model 2 compared to model 1 than the AIC did. So AIC changed 2 units, BIC changed 5. Remember that BIC is more conservative. It's going to be more difficult for you to convince BIC that a model is doing better than it will be for you to convince AIC. So in this case here, comparing the default model and the compound symmetry, we see that for both metrics, it was a worse fit by having the compound symmetry correlation structure because it took 1 degree of freedom, and because the correlation was too small, that correlation did not help to improve the model fit, so it became a worse fit. All right, I want to give you a moment just to take this in. I know it's a lot of information, and I want to open up if you have any questions.
It's more conservative was the BIC, right?
Yeah, BAC was more conservative. Yeah. So this is basically saying, I mean, both of them are saying that compound symmetry was a worse fit, but you can see that you can see that AIC was a difference of just 2 units, whereas BIC was a difference of 5 units. So BIC is telling this model is 5 units worse than the previous one. AIC is saying it is just 2 units worse. So AIC is more lenient, BIC is more conservative. The decision of which one of those you use, if they, in this case, they're agreeing, right? So it doesn't matter if you say, I chose models based on AIC or BIC, it's not going to change. But if they differ, if one of them says the model improved, the other one says the model was worse, then you have to make a decision on which one you use, which one you report that you use to make your decision, which in your paper you should say, right? So we're going to see papers saying model selection was performed based on AIC or on BIC. You have to make the decision. I think it's going to be up to you. There's really no wrong answer as long as you report what you did and what happened after that. Okay, I think I just have a lot of text here to explain what I just said in words, so I'm not going to just repeat that. All right, so maybe let's do this for one more model, which is the general, and then we'll stop here and continue on Thursday. And I also want to take a quick moment to tell you about the midterm project. All right, so to do this for the next correlation structure, which is the general one. If you recall from the lecture, compound symmetry is the simplest, general is the most complex. Now with general, we're allowing the correlation structure of all of those time points to change to a different number, where compound symmetry was saying, okay, I let you calculate a value of rho, but that value is going to be the same for all time points. Now, general is saying each one of those pairs of legs, so 120 to 130 days after planting, 120, each one of those pairs of those 4 harvest times can have their own correlation value, their own row value, which is with with this correlation structure called general. So it is the most flexible perhaps. All right, so I left you some space there for you to bring in the correlation argument. And then we're just gonna type here, the correlation argument is called core sim, which can be very confusing because core comp sim is the simplest, core sim is the most flexible, the most complex. So make sure you get that right. I was playing with the code, and if I do specify the form equals tilde DAP here, it doesn't run well on my side. So this is the only one that we're not going to be specifying the form, just so you know. So this is what you should be seeing on your side. If you run it, it should run all right. I hope. If it doesn't run for you, let me know. Because one note here that's going to be very important, we talked about in the lecture, is because this correlation structure is the most complex, it may not run, it may not converge for all data sets. So maybe if you try this on your data set, it may not converge because it is the most complex, it is estimating the most number of parameters, and therefore you may have convergence problems. In my case, I didn't. I guess no one had because I'm not seeing any confused faces. It did? Yeah, I mean, that's the case. I mean, that's the goal, right? I mean, if you don't get any errors, like it just goes through green, it converged. And that's what I'm expecting here. But it could, I mean, I guess I was just saying, like, when you do this on your own analysis, if this does not converge, it's probably because of that. Because the most complex one is the one that estimates the most number of parameters, and therefore sometimes it may not converge. Which is okay, then you just leave it behind, and that's what it is. Okay, so if we just print it just to inspect it, it's a very similar output, right? So it gives us the fixed effects first, the random effects afterwards. And now look at the correlation structure. So it's telling us that is the general correlation structure. And before we just had one value here, which was a row. Now we have 1, 2, 3, 4, 5, 6 values, which are all the values between our different times of harvest. So again, you see that compound symmetry estimated 1 correlation, general estimated 6 different values, depending on what's the difference between the harvest points. So again, the most complex one because it estimates the most number of parameters. All right, so let's check the ACF plot. I left you the code there. So, you know, at lag 1, it's just under the significance level. At lag 2, it's under it, and at level 3 is actually, it seems to me that is over, right? It's beyond the significance level. So the way that I would interpret this is that lags 1 and 2 were properly modeled, lag 3 was not. So there's still some residual correlation that that general was not able to account for on the last lag, which is again the last harvest time. All right, let's see what happens here. If you can get the intervals to run or not. I did not. It did?
Yeah.
All right. Well, I'm not sure what's going on, I guess. Yeah,
Yeah, earlier error was on.
it didn't run.
Okay, so it's opposite. On whom it worked earlier, didn't.
Well, we just have to be pairs then, right? So we can learn from each other. Yeah, I'm not sure again why we're getting these differences, but for those that did run, I'm assuming you got a lower estimate and upper for each one of those correlation values, right? I mean, if yours did not run, maybe take a peek at one of your neighbors that did run. You should see that now. Okay, let's see. I was able to run the intervals. Okay, Austin was able to, and Saker as well. Yeah, I don't know what's going on here. But I guess we're just gonna keep moving along. Okay, so on the side of those that this did run, I think you probably have 6 correlation values estimated. and then you have 6 intervals. Can you tell me how many of those 6, the interval does not contain 0? So either the lower and upper are negative, or the lower and upper are positive. If you have lower negative, upper positive, then the interval contains 0.
In lower, we have one positive, smaller than a negative.
No, but you want to compare in the line, not in the column. So one out of 6 correlation parameters did not contain 0, so only one of them was significantly different from 0. The other 5 contain 0, right? So this is just giving us an idea again that even though it's very flexible, but there's probably very little correlation with these errors to begin with. All right, so if we just now go to the ANOVA function, let's take a look at this here and take another look at it, which I think now is going to be a very interesting one. So now we have all 3 models. We see that degrees of freedom of the model 3 gen is more because again, it is estimating more parameters, so it is consuming more degrees of freedom. However, if we look on the AIC column, the AIC value for model 3 is lower than the default. So if we use AIC to decide, model 3 is a better fit to this data than it was the default. And then also what it was the compound symmetry, which was worse than the default. Now, if we look at BIC, things change. Now, BIC is telling us that this is the worst model actually of the 3, right? So BIC is telling us it did not only increase the BIC value, which again is worse, but it was the worst of all 3. So different interpretations depending on the metric. All right, I think we can stop here. It's a good stopping point. So make sure you save your script. Make sure you stage, commit, and push. So on your Git pane, you can stage everything. Commit, so we can write here, repeat the measures, part 1 perhaps. Commit, and then push. Make sure you push it. Let me open our GitHub repo for attendance. And claim your attendance. If you need to go, please feel free to go. I just want to take maybe 3 more minutes here to talk about the midterm projects. So I will send you maybe today, maybe tomorrow, a Google survey for you to tell me if you do have experimental design data you would like to analyze for this project. I think this is a great opportunity for you to run this analysis on your data, get some feedback from me. Even if you have issues that we did not cover, I can give you resources that you can explore, and you can, try to go beyond what we're learning in class. But because it is going to be your own data, I hope that's a motivation for you to learn outside of what we are learning here. So I will send you a survey asking you to tell me if you do have that type of data. And if you do, I want you to describe me a little bit more. So I want you to tell me what is your treatment design, what is your experimental design, how many reps you have, and what's your response variable, and whether or not you have repeated measures in that analysis, okay? Once you do that, those of you that respond, I do not have this type of data, this will be a project to work in duos, in doubles, 2 people in a team. I will assign it to a team. You're not going to select your team. If you do not have this type of data, but you have a certain interest, you can tell me what is that interest, like it is soil fertility, plant breeding, forages, corn, whatever it is. I mean, controlled environments. Tell me your interest and I will do my best to pair you up with someone that has a similar data set that you can work with. If I cannot find that person, then at least you're gonna have to pair up with someone that is not fully related to what you do, but at least I want you to work in pairs. And I will give you more instructions about how to do this. But the goal here is that you work in pairs and you use GitHub for that. Why am I asking you this? Even though it may be, so if you're a pair with someone that does not have a data set and you may be wanting to do a lot of the work because it is your own data. I do want you to work together. The way that I'm going to know how much you work together is going to be through your commits. I'm going to look at your commit history. I'm going to see if only one of you did everything and one person edited the README, well, that person's not going to get a good grade. So we'll check you on your commits to see who did what, when, how much. My goal is for you to work together. This can look differently. I'm not going to tell you how to work together, but you do have to put similar amounts of effort into this work. This is going to be due, I haven't decided the due date, but I'll give you at least a couple of weeks. So you're going to have time to work on this. It should not be extremely complex unless you have extremely complex data, which could be the case. But just to let you know, that's my plan for this. I will send you the survey sometime today or tomorrow, and then the instructions on how to get started, what I want you to answer, how I want you to report this midterm projects. All right, that's all from my side. Anyone has any questions?
Will we have class time to work on this project, or will we be out of class only?
It's gonna be out of class. Yeah, if we have a lot of questions like errors, things going on that I think it's worth spending our class period to troubleshoot things, then we can do that. But otherwise, it's gonna be off class. All right, I think that's all. Thanks, everyone. And sorry I kept you for a little bit longer. And I'll see you on Thursday.